What I'm going to do in the next hour is ridiculous, right? In the next hour, I'm going to teach you the basics of R programming. I'm going to teach you how to explore, clean, manipulate, describe, visualize, and analyze your data, all in the space of 1 hour. So let's do this. Giddy up. Now, importantly, everything that I'm doing, you can repeat and replicate at home because I'm only going to use data that you have access to right now. So you might not know this, but built into R and Rstudio that what you're looking at right now, there are built-in data sets that are there for you to practice with, and those are the data sets that I'm going to be using. Okay, so let's do this. Boom, shakalaka. Okay, let's go through what it is that we're going to cover in this video, and you'll see why it is ridiculous that I'm going to get all of this done in 1 hour. So you've got to stick with me. You might want to get an extra cup of coffee. Okay, we're going to talk about the basics of R. Of course, there's the 4 quadrants, how to get help when you need it, objects and functions, very important. There's built-in data sets in R. I'm going to show you how to access those, and you can use those to practice. And then packages, super important because they expand the vocabulary that's within R. How to explore your data set. You need to be able to look at the data structure and types of variables. You might want to look at what variables you've got, unique categories within factor variables, and missing data. Fine. Cleaning your data, we're going to talk about how to select variables, change variable orders, change variable names, change variable types, change factor levels, filter rows, recode data, dealing with missing data, and dealing with duplicates. We're also going to talk about manipulating data, create and change a variable using Mutate, conditional changes using if-else, reshaping your data with pivot wide, reshaping your data with pivot longer, describing your data, right? So that's the next step. Numeric variables, we've got the range, centrality, variance, summary, tables. Not a problem, easy going, easy peasy, lemon squeezy, keep going. Visualize your data. We're going to talk about bar plots, histograms, box plots, density plots, scatterplots, and smooth models. Super duper easy to do in R, and it produces lovely data visualization. You're going to love that. Then we're going to talk about analysis, and we're going to go through hypothesis testing and apply that to t-tests, ANOVA, chi-squared, and linear models. And I'm going to show you examples of all of these. Can you see how much we're going to cover in 1 hour? Unbelievable. Let's get going. Okay, so the first thing we're going to do just quickly is talk about Rstudio. We've got these 4 quadrants. Top on the left is where you write your code. So if I write some code here and push Control Enter, it'll run that code, and you'll see the code running below that in what's called the console. The console will not only be the place where you see the code running, but it'll also be the outputs of your code will pop down into the console. So you'll see that. Top on the right behind me, so you can't see it at the moment, but that's what we call your environment. If you create an object, a data frame, a variable, it'll sit there and you can see what's there and you can see some of its characteristics. You can click on it, open it up, have a look at it. Super duper easy. Below that, you've got plots. You've also got your help. You've got files. Files is basically a window in on your hard drive. So you may have data somewhere that you want to fetch. You can see that in files. Okay, these are the 4 quadrants. You can move them around with your arrows. Pretty easy and intuitive. Nothing more to see here. Okay. Got it? Of course you do. Let's keep going. The next question is how to get help when you need it, right? And you can, with anything in R, you can just put a question mark in front of it and push Control Enter, and voila. In this case, mean is a function, right? And at the bottom on the right, it's given us basically how to use that function, what the arguments within that function are, etc., etc. Same, check weights is a data frame that is built into R that you can use to practice. Push Control Enter there. Here is information about that data set, what each of the variables means, etc. There's also web pages that you can go to with lots of information and help. There's Stack Overflow, which is a place you can go to and ask questions, and there's a community that'll provide you with answers. So lots of help out there. There's a huge community of very enthusiastic people. They'll provide you with those answers for free. It really is quite remarkable. Okay, let's get into the very, very basics, right? Most of you will know this, but I'm just going to run through this. This is 30 seconds. Of course, here in the source, you can put 5 plus 6, right? That gives you, voila, 11. Of course it does. You can use R like a calculator. We can also assign the value 5 to the letter A. We're creating a little object, and we assign 6 to B, and then we can say A plus B. And of course, once again, we get 11, as you would expect. Voila, boom shakalaka. We can apply A and B as little objects. We can apply a function to them. In other words, our function here is sum, and the arguments within that function are A and B. And once again, voila, we've got 11, as you would expect. We can also take 5 and 6 and join them together in what's called a concatenation, right? We use the little C, open brackets, and they don't have to be numbers. You can put words in there, it's fine. And then we assign all of that to this variable, which is now an object called ages, right? And if we call ages by running it, we can see we get a 5 and a 6, and we can say sum of the ages, and voila, of course we get 11. Easy peasy, lemon squeezy. We can do the same thing with names, right? Names, John and James. And now we can create a data frame. We take ages, we take names, and we apply to them this function called data frames. We're making a data frame, and we take this entire line and we're assigning it with this little arrow to a new object that we're creating called friends. And voila, now we've got friends. I'm going into my environment, I click on friends, and we can see it'll pop up here. We can see John and James, age 5 and 6. Got it? Of course you do. Let's keep going. Now, if I use the function view with a capital V, I'll just run it. You can see what I mean. It brings you back here. You can always view a data frame that way. If I push str, that stands for structure, friends, we'll see what that data frame is structured like. It says we've got 2 observations, 2 variables, and the first variable is called names. It's a character variable, and here's some of the data that's there within. Same with ages, numeric, 5 and 6. Got it? Of course you do. Let's keep going. Now look, if we take the data set friends, we can use a $sign to say we want to look at a particular variable. So friends and ages, and we'll see 5 and 6. Friends and names, we'll see John and James. Of course you do. Now, this is just something I want to show you as well. You can use these square brackets to subset very specific parts of your data frame. Before the comma are the rows that you want. After the comma are the columns that you want. So if we say friends 1 and 1, it'll just row 1, column 1, and that's just John. If you leave either of them blank, if you leave the columns blank, it'll give you all of the columns for that row or all of the rows for that column. Okay, I just wanted you to see that. You'll see this notation. I wanted you to know what it means when you do see it. I don't use it that much because most of what I do and the subsetting I do within the Tidyverse, and you're going to see how that works in just a second. And that is super duper exciting, and it's easy and it's intuitive. Okay, let's keep going. Now, I told you that R has got built-in data sets, and these are the data sets that I use when I teach so that you can replicate what I do at home. If you say data, open and close brackets, you get a list of all of the data sets that are in R, and you can use any of these to practice your data analysis and your data visualization. If you say view and you put in one of the data sets there, you will see that particular data set. Here's Star Wars. I like this one because it's got lots of unique rows, lots of variables that are very sort of intuitive and easy to understand. Now, the next thing that you need to know is there are these packages. Tidyverse is the best one out of all of them, and I mean that because the Tidyverse it's a sort of collection of packages. Now, when you install a package, it expands the vocabulary within R, and you only install it on your computer once, and then it's done. You never need to do that again. So I'm not going to run that line of code because I've done this before. But when you write your code, you've got to use library and tell R that in this code we are going to be using the language and the vocabulary that exists within that particular package. So you need to say library Tidyverse. Tidyverse is like a collection of packages. It's highly recommended. There's lots of other packages, of course, and that really does make R extremely powerful. Incidentally, it's when you install packages actually and you call them with library, it expands the number of data sets that you've got available to you to practice with. Okay, so remember I showed you the data sets that are built into R and they're there. But for example, when you install the Tidyverse, you get additional data sets, and Star Wars is one of those. Star Wars is one of the extra data sets that comes with, for example, the Tidyverse. Now let's take a look at what the Tidyverse does for us in terms of making it much more intuitive to filter and select and arrange our data. And I'll just walk you through this code and you'll see exactly what I mean. Okay, I'm going to change that and you'll see what I'm doing in just a second. I'm starting off with my data set Star Wars. The next thing you see over here, and this might seem a little bit confusing, like what is that? That's what we call a pipe operator. And you can get that, you can write it out like that, but you can push Shift, Control, and M, and that produces pipe operators. Shift, Control, M. Right. The pipe operator basically just means and then, right? So it's going to take what's on the left and pipe it in to the next line of code. Okay. So we start off with our data frame, Star Wars, and then apply this function. And into that function, the first argument in the function is whatever was being piped in, right? So we're saying Star Wars and then filter Star Wars and filter it by this set of criteria. We want only observations. Filter is about the observations, the rows, right? Filter out for only observations where height is more than 150, mass is less than 200. Got it? And then, well, mutate. Mutate means change. And what are we going to change? We're either going to create a new variable, in this case we are, or we're going to overwrite an existing variable. So I'm going to say height in meters is equal to height divided by 100. Let me just show you what it is that I'm trying to do there. Right. If I get the Star Wars data set up here, here's the Star Wars data set. As it stands at the moment, we've got a variable called height, but height is in centimeters. Right, so what I'm doing is I'm saying, look, I want to create a new variable, and I want to call it height in meters, and I want it equal with each row, I want it to create a value that is equal to height divided by 100, which is going to give me height in meters. Right, so we're filtering by those criteria. We're mutating, creating a new variable called height in meters. And then, then we've got select. Select tells us what variables we want to work with, what variables we want to include in our output as the data frame we want to work with. In this case, I just want to work with my new variable that I've just created called height in meters and mass, right? And then arrange all of the data by mass. In other words, it'll do it either biggest to smallest to biggest. If I put a negative in there, it would do it biggest to smallest, but without the negative, it'll make it smallest to biggest, and then view. So let's just look at what happens then, and voila, there's the data frame, height in meters, and you can see this is all in meters, mass next to it, and everything is arranged smallest to biggest by mass. Easy peasy lemon squeezy. If you put and you can always put a hashtag in front of something and it won't run that line of code. If instead of view, I said plot, and I ran that, it would take the same data frame and make a plot for us on the right over here at the bottom. Got it? Okay. Boom shakalaka. Let's keep going. Okay, let's talk about exploring your data set, right? This is important. We've got data. We want to get a sense of the breadth and the depth of it, what's in there. Explore your data set. The first thing we want to know is the data structure. So there's a data set. It's a very nice one called M-Sleep. It's about mammals. We can look at it and we can see here the names of all the mammals. And then we've got information, categorical information about each mammal, and then some numeric data about their sleeping habits. Okay, quite a nice data set to play with. And as I say, you've got this data set, so use it and practice. Now, Glimpse. Glimpse is a lovely way to see a quick overview of that data. We can see here, it gives you the names, the types of variables, and then a little bit of data about each one of them. If you push head, M-Sleep gives you the first 6 rows. And it doesn't give you all the variables. There's more out there. But that just gives you a quick look at it. Now, class M-Sleep name. Okay, the $ tells you which variable you're looking at within that data frame. Class is lovely because it tells you that is a character variable. Fair enough. Length of the entire data frame will give you the number of variables, and length of the data frame, but a variable name included, will tell you how many observations in that particular variable. Right. Names. This is useful. I like names because if you say names M-Sleep, down here it's going to give you all the names of the variables. And the reason that's useful is you can cut and paste. You can copy and paste that into your code when you want to. So you don't make spelling mistakes, because making spelling errors is like really gives you a headache. Unique. Okay, now look here. We've got a variable called vor. Within that, that's a categorical variable. So there's herbivore, carnivore, omnivore, maybe there's others. What are the unique categories in that factor? Push unique and it tells you carnivore, omnivore, herbivore, NA, that means not available, that's missing data, and insectivore. Very interesting. Just so that you get used to this other kind of notation, we can create a little object called missing. Now, complete cases will give you, for M-Sleep, all of the rows of data within which there is no missing data whatsoever. If you push inverted a little exclamation mark before complete cases, it'll do the opposite, right? That always means the opposite. So now we're creating an object called missing that has every row that includes at least one missing value. So that, and now we can say M-Sleep, and we remember I was telling you about these little square brackets before the comma is what rows to include, and we can stick into that this object, which basically includes, all of the rows where there is missing data, and voila, that's giving you all of the missing data. There's other ways to do that, and we're going to look at missing data in a little bit more detail later on in this video. Stop watching the video. I want to give a quick, big thank you to Nested Knowledge for supporting the creation of this video. Nested Knowledge have a platform that supports the entire process, from designing your research question and search parameters to screening, tagging, and extracting the appropriate papers. The platform automatically generates visuals that you can use for qualitative analysis. So check out these interactive sunburst diagrams used to get an overview of trial endpoints. Or, and this is going to blow your mind, it can extract study results to do meta-analysis. So check out these ready for publication forest plots. And this next amazing feature is going to become, I believe, the new standard for systematic review. It's being able to publish a living document that auto-updates as more data becomes available. So check them out by clicking on the link in the description below. Okay, let's get on with the video. So we've got a sense of our data set, but we might want to clean it up. In other words, we might need to kind of, select the variables that we want to select, the rows that we want to look at. We might want to deal with missing data and duplicates. Okay, so let's take a look at some of these features. Star Wars, and then now select tells you what variables you want to look at, right? So in this case, we're saying select name, height, and mass. What happens then? Voila, name, height, and mass. Fair enough, super duper easy. We could also say select 1 to 3, and it does the exact same thing. So you can use numbers. We can say select ends with color, and I'm actually going to delete that there, and then hair color, skin color, eye color. So it just selected variables where the variable name ends with color. You could also say starts with, contains, etc., etc. Okay, that's pretty easy going. You can also use the select function to change the order, right? So if we go up here, we've got name, height, mass. We could, if we just say select name, mass, height, it'll put them into that order. And then you can put everything open and close brackets, and it's basically going to provide you with everything else. I'm not going to say view. I'm just going to do it like that. You can see that it's got name, mass, height, and then everything else. Okay, just as advertised. Let's keep going. You might want to change the name of a variable. Well, we've got a function called rename. So all you do is Star Wars, that's the data frame, and then rename. You start off in inverted commas with the new name of the variable, and then it is equal to, and you put in the old name of the variable. And then I'm saying, and then head, it'll just give me the first 6 rows. And what was name over here is now characters. Fair enough. There are times when you might want to change the type of variable, right? So if we say class Star Wars hair color, we can see that hair color is in fact a character variable at the moment. So it's just basically a set of characters. R hasn't identified it as a factor or a categorical variable, right? We can change that. We simply say Star Wars hair color, right? And what are we assigning to this? We're basically going to overwrite. Star Wars hair color already exists, but we're going to overwrite it by assigning what is ever to the right of the arrow to that variable, right? We're using the function as character and applying to that function. We're basically taking Star Wars hair color, right? So we Star Wars hair color, apply the function that, and write over the previous version of itself. And if we do that and then run class Star Wars hair color again, we now have a factor. We can also change we can change a variable type using the Tidyverse. We say Star Wars and then mutate, which is the same kind of idea. Mutate is create new or write over. Hair color is equal to as character, because at the moment it's a factor. We want to change it back to a character just for the sake of illustrating this. Hair color, and then, and I'm going to say glimpse, because glimpse allows us to have a quick look at this. Hair color is now back to a character. Easy peasy, lemon squeezy. Right, factors can have level. Well, the factor always has a level, but it sometimes matters what the level is. In other words, our default will be to make the factor levels in alphabetical order, right? So let's have a look at this as an example. And the reason that's important is there are times when the order matters, right? Small, bigger, biggest, for example. The order that the factors are in does matter some of the time, not always. So if we say, I'm going to create a new data frame, DF, which is, and I'm going to assign to it data frame, Star Wars, and then sex variable, I want to make it a factor, so as factor, data frame sex. Now, if I ask for the levels, can you see down here? It's done it in alphabetical order as we expected. Female, hermaphroditic, male, and then none, right? So that's what it's done. Now, we might, if we wanted to change that, how would we do it? Very easy to do. We take data frame, we're going to write over it, assign to data frame, and then mutate. Sex is equal to factor sex levels. Now, basically, we're just saying levels equals, and then you put the levels into whatever order you really want them in. I've got all the closed brackets at the end of that. On the next line, it doesn't matter where you put them. And then if we say levels, sex again, now it's in the order that we wanted. Male, female, hermaphroditic, and none. Okay? Easy peasy, lemon squeezy. Right, we spoke about select. You use select to identify the columns that you want, the variables. Filter selects the rows that you want. So it filters out the observations against some sort of criteria, right? So filter, let's have a look at that. For Star Wars, I've just said select mass and sex, just so that we're just dealing with two variables, just to make the outputs easier to understand. Now, here we go, filter. We want filter, mass is more than or is less than 55, and sex is equal to male. We use two equals here, and the reason is we're asking a question. We're not making a statement that sex equals male. We're saying where it is the case that sex equals male, include that observation in our filter, right? So that we use a double equal sign there. And if we run that, you'll see mass is always less than 55 and sex is always equal to male. Got it? Okay, let's keep going. You sometimes need to recode data. Okay, so for example, we may, in our data frame, we may have males and females, and we want that to be changed consistently to man and woman. Easy to do. Star Wars, select sex. Again, this line of code isn't necessary for what we're trying to do, but it's just going to be easier for me to show you in the output what we've accomplished. Mutate, we know what that does. We either create a new variable or we write over an existing variable. In this case, we're going to write over sex, and we're going to take the function recode. We're going to apply to it in the first argument the variable sex. That's what we're using. And wherever it sees male, it's going to change that to man. Wherever it sees female, it's going to change that to woman. And there you go, man, man, woman, woman, etc., etc. Let's quickly talk about dealing with missing data. Okay, now first of all, if I remove this little bit of code over there, okay, if I want to take the mean of Star Wars height and I try and run that, you'll see that I just get an NA, right? It's unable to run that. It's unable to apply that vector to this function. And the reason is there's some missing data. And this function mean doesn't know how to deal with missing data. So we add in a little bit of code that says NA, which means not available, RM, which means remove, equals true. NA remove equals true, which means it will remove NA values from that vector when you run that line of code, and voila, of course, now you get an answer 174. Got it? Okay, let's keep going. To talk about duplicates, the data frame that I have at the moment has no duplicates in it, so I'm just going to create a new little data frame, names and ages, and create a data frame called friends with names and ages, and have a look at friends. And look here, we've got Peter, age 22, appears twice. Very easy to get. If we say friends and then distinct, voila, we've got Peter, John, and Andrew, no duplicates. Super duper easy. That's the same as going distinct and putting friends in the friends object, which is a data frame, in as the argument, and exactly the same output. Next, we're going to talk about manipulating your data. And some of this is going to be a bit repetitive because you would have seen a little bit of this already, right? First, we're going to talk about mutate. Now, we've used mutate a few times already in this lesson, so this isn't new to you. We can mutate the first argument. Let's have a look at this. Star Wars, mutate. Now, you can either overwrite height or you can create a new variable called height in meters. Right now, if I'm just going to get Star Wars on the screen. Star Wars. Right. Can you see height is in centimeters? And we've basically we're creating a new variable called height in meters, and we're making that equal to height divided by 100, and then if we select name, height, and height in meters, voila, we got name, height, and height in meters. Can you see the difference? Okay, super duper easy. Let's keep going. Now we can make a conditional change, right, using if else, and let's have a look at how to do that. Let's say, for example, we wanted to change our height in meters into short and tall, like categorize them somehow. Not difficult to do. Again, all of this is the same. Height is equal to height divided by 100, right? Select height and height in meters. Fine. Now, mutate. Let's create a new variable called tallness, and that's equal to if else, right? In other words, we start off with some sort of conditional question. Height in meters is less than 1. And if else works like this. If that is true, then replace with the word short. Else, replace it with the word tall. Okay, and let's run that and see what happens. And voila, we've created a variable called tallness, and we've got tall, tall, short, short, tall, etc., based on the value in that variable right there. Okay, now reshaping your data. This is actually very important. So pay attention. This is a little bit more tricky than a lot of the stuff we've been dealing with, but it's really useful if you get your head around it. Gapminder. Gapminder is a lovely data set. If you push install packages, Gapminder, then library pack Gapminder. I don't know if I've called it today, so I'll just push that. It's got a data set in it, and let's have a look at that data set. Countries, continents, years, life expectancy, population, GDP per capita. Lovely data set to work with. Now, this, as it is at the moment, is what we call it's in a long format. But you can imagine having the same data where the years were all variable headings. Okay, so can we get this data frame into that shape? And the answer is yes, we can. Right, so let's first of all create a data frame called data. And that data we're going to assign to it from the Gapminder data set. Now remember, we could have gone Gapminder and then select. But if you don't do that, you can put Gapminder in just as the first argument. Okay, just to let you know. And we're going to select country, year, life expectancy. Okay, so if we control enter that and we click on data, you can see that's the data frame that we've got now. Okay, now view data, that does the same thing. Now, here's where we pivot wide. We're going to create a new data frame called wide data, and it's going to be, we're assigning to it data, and then pivot wider is the function that we're using, and there's two arguments you need to put into it. Names from, and basically the new variable names, where's it going to get those names from? And if we look at our data, we want to use these years to create names, okay? And so it's going to names from years and values from life expectancy. It's going to use these values in the cells underneath years. So look at what we've got here. We've got countries, and we've got Afghanistan and all the different years and the life expectancy. And if you go down, then you've got Albania, and you've got all the different years. You've got the same years really and life expectancy. Right? Look at what happens if we run this code and then have a look at that. Voila. Now we've got Afghanistan, and all of the years are column headings or variable names, and what was life expectancy are inside the cells. Super duper nice, isn't it? Okay, and easy to do. Now going backwards is just as easy, right? So now we want to create a data frame called long data. We take our wide data, and then we use pivot longer. Now we need to say which columns we're going to be changing, right? So it's 2 to 13. Names to a variable called year, values to, and inside the cells we're going to create a variable called life expectancy. So run that, and we've gone back. Names to, so what were names? All of the variable names have gone into a new variable that we've created called year, and all the values that were in here have been assigned to a variable called life expectancy. We could have called it something else, by the way. I've just used the same names as were in the original. Let's talk about describing your data, right? We're going to look at the sleep data, and that's our data set. We want to describe it. Where we've got a numeric variable like awake, that's the amount of time that any of these mammals are awake. First of all, we describe numeric variables for statistical purposes in terms of the range and spread. So we've got the minimum, the maximum, the range, and the interquartile range, and I'll just run each of those, and you can see those values pop up in the console. Super duper easy. Okay, centrality, the mean and the median, you could add the mode to this for the same variable, and we've got the mean, the median, they're both 13. I'm not going to waste time. You guys know what I'm talking about there. And the variance, exactly the same. There's the variance at the bottom. All right. Now, we could say summary, sleep, awake, and it provides us with all of those in one file swoop, right? Minimum, maximum, interquartile range, median, and mean. Okay, that's quite nice. Or we might want that for two variables, right? We want to sleep, select awake and sleep total, and then summary, and voila, we've got all of that data for those two variables right there. Okay, nice and neat. Now you can create summaries yourself. Okay, now what I'm going to do, I've got some code here, and I'm going to first run the code so we can see what it is, where it is that I'm going with this, and then I'll walk you through the code so that you understand how we got there, right? So I'm going to run it, and we'll look at what I've created. I've created a table, and the table, all of the data is being grouped into the categories in the vor variable. So we've got herbivore, carnivore, omnivore, and insectivore. So we've grouped everything by and within each of those groups, I've asked for the lower, which is the minimum value. Upper, I've just called it the maximum value. The difference between the two is that, and the average or the mean is this. So I've created 4 columns, and for each of those columns, I've defined what goes into these cells as categorized or as sort of grouped by, the categories in the var variable. Does that make sense? So we've got var, and they represent sort of row headings in a way, and I've created column headings, new column headings. These didn't exist in the data set, and I've calculated something inside each of those. Okay, so how did we get to this? Now that you know where we're going, the code will actually be quite easy to understand. But I wanted you to see this first. So let's go back to the code. Okay, we're back at the code, right? We started with msleep. The first thing I did is I dropped the missing values from var. That's just going to simplify our table a little bit. We didn't have to do that. Just it's good practice in this set of circumstances. Then I've grouped by var, and group by and summarize work quite nicely together. Then I've got the function summarize, and next to summarize, here's where I create my variable headings or my column headings. I say lower, and that's going to be equal to min, which is an existing function in R, and the variable that I want the minimum of, sleep total. Average, mean sleep total. Upper, max sleep total. Difference is equal to max sleep total minus min sleep total. And then arrange by average. I just want that's order, and then view. And if we run that, voila, we go back to this. Got it? Okay. That's really nice. That's a really, really nice function. Let's talk about creating tables. There's a table function, which is convenient. So if we say table msleep vars, it's going to give us just a count basically within each of those categories, how many observations fit into those categories. So that's pretty easy to do. We might want to know for each of these vars, how many of them are rodents and how many of them are primates. Well, let's look at how to do that. Take msleep. Select vars and order, right? Order is the order of mammal, right? Filter. Now, this you haven't seen this until now, and I thought I'd just quickly show you this. There's more than one way to filter, and this is kind of a nice little trick. If we're wanting to include a number of possible values in our filter, we can say for the variable order, if any of these inside the concatenation are in that, then include them, right? And then create a table. And voila, we've got primates, rodents, basically, and our carnivores, herbivores, omnivores. Got it? Okay, let's keep going. Okay, now we're going to talk about data visualization. R is particularly powerful when it comes to data visualization, and it's really worth getting to know and understand how it does it, because you get so much latitude, you get so much space, you get so much capacity to be creative and do visualizations that you really, really like it. You're able to tell the story. So of course, there's just base R. So before we start using packages, there's base R, and we can say plot and pressure, and voila, R produces a nice little diagram. Super duper easy, but we want to move past something like that, and we want to create much more sophisticated diagrams. The first thing that I want you to understand is there's this idea that's been invented called the grammar of graphics. And basically what you want to do when you think about graphics is think about what data you're using. I suppose that's obvious. Mapping, and I'll tell you what I mean by that in a minute, and geometry. And you want to think about these three things, and then you can create layers, and you can do all sorts of interesting things, but you want to think about these three concepts. Data is pretty simple. We're going to be using a data frame at any point in time, but you have to define the data. Fair enough. That data will have variables. Those variables can be mapped out against certain aesthetics. In other words, what are the aesthetics on your canvas? And this is what they are. Well, first of all, there's the X and the Y axis. So a variable might be mapped out against the x-axis, another variable might be mapped out against the y-axis, and you can see that in this example here. Temperatures on the x-axis, pressures on the y-axis, and our data points are on the canvas itself. Each data point has both a temperature and a pressure. So these two variables, temperature and pressure, have been mapped out against the X and the Y aesthetics. But there are other aesthetics that you can apply to the same canvas. For example, color, shape, size, etc. So there's a lot you can do if you understand the idea of aesthetics and mapping a variable against an aesthetic. And you're going to see as we do a couple of examples why that's kind of quite an exciting concept. And then once you've mapped that, you've said this variable will be mapped against that aesthetic, you can start applying geometries. And what do we mean by geometries? Geometry can be a line, it can be a bar chart, it can be a histogram, it can be, there's any one of those kind of shapes that R can produce. You just define the geometry and it will, and you'll see how the aesthetic and the geometry start working together to produce absolutely beautiful plots. Okay, let's do a couple of examples. Okay, in each of these examples, I'm going to add something new to learn about data visualization. So we're going to start off with a super duper easy example. ggplot is the package that we use it's ggplot2 actually, but we just use the function ggplot. We use ggplot to create these graphs. That package is included in the Tidyverse. So if you've installed and called the Tidyverse, ggplot is there on your computer. You don't need to call it, right? We said, first of all, we define the data, and that's equal to Star Wars in this case, comma. And I go to the next line, but you could just carry on the same line. Mapping, that's what we talked about, mapping, okay, is equal to, and this is where you define your aesthetics. And in this case, I'm just going to define one aesthetics, X is equal to gender. And now we don't use the pipe operator, we say plus, right? So first of all, in our ggplot, we define the data and the mapping, and then we add to that, the plus, the geometries, right? And in this case, geom bar, that's going to be a bar plot. And if we run that code, we're going to see a bar plot. Okay, pretty easy. Gender and basically a bar plot produces a count. It's included the missing values NA. Fine. Okay, let's get slightly more sophisticated. Now, instead of saying ggplot and data equals, I'm going to pipe the data in using our pipe operators. So I'm starting with Star Wars. And the reason piping it in is quite a useful thing to do is that you can do things to your data before it gets into the graphic, into ggplot. So you can manipulate it. You can remove missing values, for example. You can filter it. You can mutate it. You can do all sorts of things with your data as it's getting piped into ggplot. And that's why this is so powerful, right? So we're saying data. And here's an example of that. I'm saying drop NA. So we're removing the height, the missing values from height. And then, now it's piping it into ggplot. Remember we said when you pipe something in, R assumes that the first argument in that function is whatever's being piped in. Right? So whereas up here we had to say data is equal to Star Wars, we don't need to say that because the first argument in ggplot is taking this piped in object, which is Star Wars, just without the missing values in height. And now we're saying mapping is equal to aesthetics. Now, again, just so that you know, you don't have to say mapping here. I've just written it there so you know what's happening. But if we removed that, it would still work. And actually, I'm going to do that just so that you can see. You can go straight into aesthetics. It knows that it's doing the mapping. Again, I'm just, at this point, defining one aesthetic, X, the X-axis. And again, you don't have to say X. It knows that the first argument is X, the second argument is Y. And after that, you've got to be a bit more specific if it's color or shape or height or size or something like that. Right. So aesthetics, height. Add to that a geometry. In this case, the geometry is going to be a histogram. And voila, there's our little histogram. Okay, let's keep going. Now we'll get a little bit more sophisticated, right? We're saying Star Wars. We're going to pipe that in, drop NA, find ggplot. Now we're mapping. Again, we don't have to say mapping. Let's remove that. We're saying X is equal to height. We don't have to say the X. It's assumed, right? Now we're adding in geom boxplot, right? So it's a numeric variable, and numeric variable, you can represent it either with a histogram or a boxplot or a density plot. There's a number of ways. So we're now going to use a box plot, and we're going to fill the box plot with a color, steel blue. And you can use, there's lots of ways to add colors, but this is a very simple one. It's just to write the name of the color in there. We're going to add a theme, and that just basically, there's some certain themes that are built into R. You can change them, you can add to them, but a very basic one is black and white. And then we're going to add some labels. Title equals box plot of height. The X-axis label is going to be height of characters. Let's run that and have a look at what it looks like. Voila. Now we've got a box plot. We've got a title. We've got a axis title that we've defined, and we've colored it in with steel blue. Okay, let's get a little bit more sophisticated, right? Star Wars, drop NA from height, filter, right? And now, because I'm going to add, I'm not just going to use height, I'm going to use sex as well. But I just want males and females. I don't want the hermaphrodites and I don't want the missing values. I just want males and females. So I'm saying filter in. Remember we said you can do this concatenation. So if you take all of the values inside the concatenation, if any of them are found in that variable, those rows will be included in the filter. And then, so we pipe all of that in to ggplot. Our mapping, we don't need to say mapping, it's assumed. So we'll delete that. X is equal to height. We don't need to say X is equal to height. It's assumed. Now we're going to add in some additional aesthetics. We're going to say color and fill. So color is the color of the lines, and the fill will be mapped out against sex. In other words, it's going to do something, and you'll see what in just a second. differently for males, observations that are males and observations that are females. Then we're doing a geom density plot, which is very much like a histogram, but it's just really the instead of the count of observations, it's the probability of an observation at any particular value. When the density plot's up and running, you'll see what I mean. Alpha equals 0.2. Basically, the alpha value is how dark the coloring in must be. Alpha equals 1 is normal, alpha equals 0 is completely transparent, and everything in between. And then again, theme black and white. Let's look at what that looks like. Voila. So because we've got an aesthetic that includes two different sex, which has got two different factors, it's basically drawn the graph twice. It's done it for males and females. It's done the line by male and it's colored it in. The fill is by male and it's alpha 0.2, which means it's mostly transparent. If that was alpha, let's just change it to alpha 1 and you'll see what I mean. If I change that to alpha equals 1 or just left it out completely, it would assume that it's 1. If you leave it out completely, you'll see it makes it nice and dark, right? And then of course the line is the same color. Okay, let's get a little bit more sophisticated. Right, here we're gonna create a scatter plot or using geom point. Right, Star Wars filter. I'm just showing you how you can filter the data as it goes into ggplot again, and then ggplot. Aesthetic height is the x-axis. Mass is, see, the second argument is usually y is equal to mass, but because y is always the second argument, you don't need to define it. You can just put it in there, mass. But for things like color, you do. Again, we're going to say color is mapped out against sex. So the x-axis is height, the y-axis is mass, and color is equal to sex. The geometry that we want to use, that's the mapping. The geometry that we want to use is geom point, so that's a scatter plot. The size of the points are going to be 5, right? That's like 1 would be small, 10 is very big. I mean, you need to experiment with that to get a sense for what that means. Alpha, we've already said, is the transparency. Theme black and white, we've discussed. We'll actually change that to theme something else, so you can see that there's minimal. And then we've put in a title. Okay, so let's run that. Okay, and the difference between theme black and white and theme minimal is it doesn't have the box around the outside, but it's kind of quite neat and clean. We didn't filter the sex by just male and female, so you can see it's done all the different colors for sex. We did filter mass by less than 200, so there's no observations that are more than 200. And each of these, right, each of these observations obviously has a height, obviously have a mass, and have a sex. And so these we know 3 things about each of these observations just by looking at them. Okay, let's keep going. Okay, we're going to get a little bit more sophisticated now, and we're going to say pretty much the same code, right? Star Wars filter, ggplot, geom point. Now we're adding in geom smooth. We're adding in another layer, right? So we're going to, on top, and geom smooth is basically, it's going to draw a smooth linear model over our points. So we're adding in an additional layer onto our canvas, geom smooth. As well as adding in the extra layer, what I'm going to do is do a facet wrap by sex. In other words, I'm going to basically say we want to look at this data in different little boxes, and you'll see what it looks like in just a second. Then again, the theme and the label. Let's have a look at that. Okay, so facet wrap basically created a new facet for each of the sexes. The sexes are still categorized by color. We've still got our height and mass as our x and y coordinates, but we've added onto it this line here, which is basically a linear model that's been smoothed out, and the gray around it is the 95%. It's not the confidence interval; it's the standard error. Okay, let's talk about analyzing your data. We're going to talk about hypothesis testing, and we're going to use examples using a t-test, ANOVA, chi-square test, and linear models to illustrate this. It's super interesting. It's quite fun actually. Okay, Gapminder, it's a nice data set. I think we've probably called it already. If we have a look at the Gapminder data set, I think we have used this actually. We've got country, continent, year, life expectancy, population, and GDP per capita. Now, this is just a plot that I've created. You can see it over here. In this plot, let's just look at the plot before we run the test, so you know what the question is that we're asking. If we look at this plot, we can see we've got it's a density plot. We've got the life expectancy in Africa, and we've got the life expectancy. This is the distribution of life expectancy across countries in Europe. And in each case, we've got an average, a mean, right? In Africa, the mean is 48. In Europe, the mean, the average, life expectancy is 7 to 1 in the time frame that the data was collected. I think it's between 1952 and 2007. Okay. What we can do, even though it's obvious when we look at this, that there's a difference in life expectancy between Africa and Europe, we can test that. We can run a t-test and test the hypothesis, test the idea that there's a real difference. How do we do that? We assume the opposite. We assume that there's no difference. That's our null hypothesis. If it were the case that there were no difference in the life expectancy in Africa and Europe, how likely would it be that we would get a sample that has a difference of this magnitude or more, right? And that is your p-value. And how do we get a p-value? Let's run a t-test and have a look. Okay, here we are. Gapminder, filter just for continents, Africa and Europe, right? Pipe that into the t-test, and we want to do the t-test looking at life expectancy as a function of continent. Data equals dot. We've talked about this before, right? The t-test wants to see the data here. The pipe operator wants to put the data right at the beginning. We put data equals dot to tell R, put the data over here, right? Now, these next two arguments, you don't need them. These are default. It's assuming we're doing a two-sided test, and it's assuming we're not doing a paired test. I'll tell you what those are in a second, but you don't need these arguments right now. If we run this data, we get a t-test, but this is the t-test. The p-value is very small, 2.2 times 10 to the power of negative 16. In other words, 0.0000000, etc., etc. A very small p-value, which means we can reject the null hypothesis. The probability of getting a sample like this, if it were the case that there was no difference in the means, is extremely small. We should define what we mean by extremely small, like what is the threshold for us rejecting the null hypothesis. Usually we use sort of 0.5, that's 5%. This is extremely small. We reject the null hypothesis. We accept the alternative, which is that the difference we're seeing in the data is in fact real. It's a real difference. It's statistically significant. Let's just talk about these two arguments here. Alternative two-sided, you could make that alternative less or alternative more. In other words, it would do a one-sided test. It would test whether or not, in actual fact, Africa has not just that it is different from Europe, but that it is less than Europe, if that makes sense. Okay. Usually we like to use a two-sided test because it's just, our starting point is, are these two things different? But sometimes you need to do a one-sided. Paired equals false. Now, let's say we were comparing just Africa in 2002 to 2007. Each of the observations in Africa in 2002, there would be one of the observations would be for South Africa, but in 2007, one of the observations would be for South Africa too. So there's a pair. All of the data, there's a counterpart in each of the arms of the t-test. And so we do a paired t-test. It just means the mathematics is slightly different. Okay? All right. The t-test lets us compare two means, but what if there are three means? What if there's three averages we want to compare? And that's what this does here. Then we do an ANOVA, right? Analysis of variance. So here we've got Europe, the Americas, and Asia. Again, we're working with our Gapminder data. Europe, America, Asia. We've got we've got life expectancy, and the big dark dot is the average life expectancy. In box plots, the line is the median. I've just stuck the big dot as the mean. Okay. And in these density plots, I've put a little dotted line for the mean in each case. It'll be a little bit easier to see. Actually, we can get that plot up if we want to have a look at it here. There it is there. Okay, so you can see what I'm talking about. Now, if we want to say, look, our null hypothesis, is there a difference in the means here? We're not saying is there a difference between this one or that one. We're just saying across these three continents, are they all the same or are they different? We do an ANOVA test. Analysis of variance. Let's look at how to do that. And it's pretty much as easy as what we did before. We say Gapminder, filter by, okay, I'm just doing 2007. It could have been all the data. Then filter again. These are the continents. We know how to do that. Then AOV, that's the ANOVA test. Life expectancy by continent, data equals dot. We've talked about that. And then summary. The summary will basically bring up a summary of all of the pertinent outputs of this analysis. So let's do that. And the one that we're most interested in is the p-value. Again, it's very, very small. So the p-value is basically telling us that if the null hypothesis were true, that all three continents have got the same average life expectancy. If that were true, it would be very unlikely, and that's the p-value, the probability would be very, very small, that we would get a sample that showed a difference that we're seeing in the data here. Okay, so we can reject the null hypothesis. We think that's not the case. It's just too unlikely. It's not, getting a difference of this magnitude or more is very unlikely. So we can accept the alternative hypothesis, which is that what the signal we're seeing in the data is real. It is statistically significant. Now we can run that same analysis of variance test, but instead of piping it into the summary, we pipe it into a 2-key HSD, and that's going to do something interesting. That gives us a little table at the bottom here that considers each of the pairs separately and gives us an adjusted p-value for that particular combination, right? So it looks at Asia and America. There's a difference of, the minus 2.8. That's just because of which one you're subtracting from which one. It doesn't really matter, but there's a difference of about 2. There's a confidence interval, and that confidence interval crosses 0. In other words, it includes the possibility, the 95% confidence interval includes the possibility that there's no difference at all, and the p-value is quite big, right? So the difference between Asia and the Americas is not statistically significant. However, the difference between Europe and the Americas, well, that's the difference. This is the 95% confidence interval, which doesn't include the value of 0. So the 95% confidence interval doesn't include the possibility that the difference is nothing, and the p-value is less than 0.05, which was our threshold. So we'd say that is statistically significant. Similarly, for Europe and Asia, statistically significant. And we can pipe that into a plot, and we can actually visualize that. And here you got Asia and America crossing the 0, but the other two not. These are the two that are statistically significant. Okay, if we want to talk about a chi-square test, now we're talking about categorical data, right? Two categorical variables or one categorical variable. There's a data set, and you've got this data set called iris, and it's got different species of irises or flowers, and petal width, petal length, etc., etc. So we're going to use sepal length as a proxy for size. What I've done here is I've chopped up the sepal length into 3. I've used the cut function, right? So mutate size. I've created a new variable called size. I've used the cut function. I'm applying sepal length to it. I'm breaking it 3 times. In other words, I've got 3 intervals. I'm labeling those intervals small, medium, and large. And then I'm selecting just species and size. And if I run that and then have a look at what flowers looks like, here we go. I've got our species, and each of them is small, medium, and large. Okay. So again, let's just look at this diagram that represents this data, and we'll get a sense of it, especially on the left-hand side here at first, we'll get a sense of what the question is that we're asking. We're going to do a chi-squared goodness of fit. In the first instance, if we just take the small, medium, and large, so ignore the different species, we could ask the question, is it the case that that the distribution, the proportion of flowers that are small, medium, and large is the same? The same proportion of small ones to medium ones and large ones. And obviously, looking at this data, that doesn't seem to be the case. How would we show that to be true? What is the statistical test? Well, it's the chi-squared goodness of fit test. The null hypothesis is that there are equal numbers of small, medium, and large. In other words, the proportions equal, and the alternative is that the proportions are not equal. So let's do a test to demonstrate that. Easy enough to do. Let's look over here. We take flowers, this new object that we created, select out just the size, because in the goodness of fit, we just want to look at one variable, just the size, and it's got to be a categorical variable. And then I'm saying, let's create a table. Now, I'm not running into the chi-square test just yet, because I want to show you the table, right? The table gives us these values, 59, 71, and 20. When we run the chi-squared test, and I'm going to take away the hashtag here so that it'll pipe the table into the chi-squared test. When we run the chi-squared test, it's going to be asking the question, are these 3 proportions the same? Are these 3 values the same? If they were the same, how likely is it that we would get the differences that we're seeing? So let's run the chi-squared test, and voila, we get a p-value, very, very small, 6.6 times 10 to the power of -7, 0.000000 something. It's extremely unlikely that if these were the same, we would get a sample that looked like this. So we reject the null hypothesis and accept the alternative that the difference is statistically significant. And the chi-squared test of independence is exactly the same idea, but now we're looking at the right-hand side graph here, and basically we've got not just the number of small, medium, and large flowers, but within each of those groups, the extent to which they are Setosa, Versicolor, and Virginica, the 3 different species. And the question is, are these things independent? Knowing the value of one of these variables, does it help us predict the value of the other? Or are they distributed across each other perfectly in the same way? Are we seeing the same number of each species in all of the small, and the same number of each species in the medium, and the same number of each species in the large? Looking at it, that's obviously not the case, but let's show that using the chi-squared test of independence. In other words, we want to show that that there is a dependence, that the value of the one variable is dependent on the value of the other. Okay, so we start off with flowers. We create a table, and I'm just going to run that so you can see what the table looks like. Here's our table. We've got small, medium, and large, and we've got our species, and we can see within each cell what those values are, right? So we want to run that into a chi-squared test, and here we go. Voila, we've got a p-value of 2.2 times 10 to the power of negative 16, extremely small. So it's extremely unlikely that if all of these proportions were the same, that we would get a sample that looked anything like this. Reject the null, accept the alternative. What we're seeing in the data is statistically significant. Okay, let's talk about a simple linear model. Okay, we're going to use a data set called cars. And if we just look at the first few values of cars, it is speed and distance. Okay, how fast a car goes and the distance that's required for that car to stop, right? And we've plotted that here. We've got speed of cars on the x-axis, distance taken to stop on the y-axis. We call the x-axis the independent variable, right? It doesn't, the speed of the car doesn't depend somehow on the distance taken to stop. However, distance taken to stop does depend on the speed of the car. So it is the dependent variable. So y is dependent, x is independent. Each of the red dots are observations. Each observation has a value, both a speed and a distance to stop. Now, when we do a linear model, this is what's happening. We've created what's called a best fit line. This is the line that fits most cleanly in the data, right? That best fit line has got a y-intercept. The y-intercept is often meaningless, right? Because the y-intercept in this case, you know, the distance to stop when the car is stopped is meaningless. But we need a y-intercept in order to draw the line. So there has to be a y-intercept mathematically. The slope, however, is important. The slope of 3.9 means for every change in 1 unit of speed of car, there's 3.9 additional changes to the distance. So increase of 1 kilometer per hour increases 3 meters to stop the car. Okay, and we see that in the slope of the line. The p-value is, I'll tell you what the p-value is here. We've got a slope of 3.9. The null hypothesis is that the slope is 0, that there's no relationship between speed and distance. If that were true, how likely is it that we would get a sample with a slope of this magnitude or more? And in this case, that would be very unlikely. A p-value of 0.000, 10 to the power of negative 12, extremely small. So it would be very unlikely, if there were no relationship between speed and distance, that we would get a sample of this with the slope of this magnitude or more. Okay, and then r squared. This is how much of the change in y can be explained by a change in x. Because, of course, there'll be other factors that influence the distance to stopping. Who was driving, what kind of road they were on, time of the day, I don't know. But how much of what the change in y can be explained by the change in x, that's the r squared, 65. So 65% of the change in distance to stop can be explained by the speed of the car. And that's how the model works. Okay, we can use a model to predict. So we can say if a car was going this fast, how long would it take to stop? And we can use the extent to which we can also determine how much of the change in y is explained by the change in x. So there's when we do a simple model or even a more complicated model, of course, there are, we call that multivariate modeling. It gives us a lot of numbers, but these are the 4 that we're really interested in. And let's look at how we do the model. We've got cars, and then the linear model, distance as a function of speed. So that's the dependent variable as a function of the independent variable. Dot equals dot, and then ask for the summary, and voila, here we go. Firstly, we've got the residuals. The residuals is the distance between any of the observations and the line, the model, and the model. You'd expect the residuals to kind of be symmetrically distributed around 0. The coefficients, the first coefficient is the y-axis. The next coefficient is the slope. We're not interested in the y-intercept in this point because we don't think it's meaningful, but the slope is meaningful, and the p-value for the slope is given right there. And then the r squared is over here. The adjusted r squared only becomes relevant when you do multivariate analysis, and the F statistic becomes interesting when you start looking at multiple variables and you want to know what the overall model is worth. But these 4 these 4 things are the most important for you to understand the basics of simple linear regression. I've created a data visualization with R cheat sheet. It's got all the code for producing lovely, lovely graphics in R. So it's free. So if you click on the link on the screen, you can download that and you can see all the code and the graphics. And I think that it's a lovely thing. It's there, it's free. Take it by all means. Please do share this video with other people that you think might find it useful. Comment below and like, of course, and subscribe to my channel if you haven't already. Hit the bell notification if you want notifications of future videos. Have a great day. Take care. Don't do drugs. Always do your best. Speak to you soon. Bye.